Hi, this video is about Newton's first law, and it's keyed to Young and Freedman's University Physics Chapter 4 in the second section. But any physics textbook is going to treat Newton's first law, I promise you that. And the Newton in question here is not a fig Newton you eat, it's Sir Isaac Newton from the 1600s. Of course, Newton himself wasn't the one to discover this rule of nature, but since he's the one that kind of collected the rules into Newton's three laws, he went ahead and borrowed this one from Galileo, which was a little before him. But I'm getting ahead of myself. Newton's first law, let's put it in easy terms you may have actually heard before. A body in motion wants to stay in motion. A body at rest wants to stay at rest. There you have it. If you're driving along and suddenly the brakes go on, your body will lunge forward. Why? Because your body wants to stay in motion. It's a body in motion that wants to stay in motion. That's why we have seat belts, so that you don't go flying through the windshield and die. And so a body in motion wants to stay in motion. The same way that if you're sitting up and somebody accelerates, hits the accelerator real fast, you're going to go kind of pushed back. Why? Because your body wants to stay at rest. It doesn't want to move forward. So a body in motion wants to stay in motion, and a body at rest wants to stay at rest. As I said, Galileo is the one that first discovered this rule. It seems somewhat counterintuitive for reasons I'll tell you in a second. But Galileo is the one that formulated this law of inertia, where inertia is that thing that wants you to keep going. The inertia is that, what we call that tendency to keep going. And so you're going to your body wants to keep going straight. If you suddenly get stopped, your body wants to keep going. If you're on a Ferris wheel, not a Ferris wheel, if you're on a merry-go-round and the merry-go-round is going around and around and around and around and around and around, if you jump off, you're going to go flying, in the same direction you are at the point that you jump off. That's inertia. And Galileo, a little bit before Newton, came up with this idea. Now here's this Newton's first law in textbook speak. So we can talk informally because this is just a video on YouTube. But Young and Freedman, they have to be professional. And so here's how they define Newton's first law. A body acted on by no net force moves with constant velocity, which could be zero velocity, and with zero acceleration. That's a fancy schmancy way of saying a body in motion wants to stay in motion, and a body at rest wants to stay in motion, stay at rest. Now, why doesn't this seem right? Well, the reason is because we're used to friction. Friction slows us down. If I roll something on the carpet, especially, it's going to slow down quickly. But even on a smooth surface, eventually it's going to slow down and stop. This is because of the rubbing, as it were, informally, between us and the ground. And so friction slows things down. But if you could get into outer space and throw a baseball, the baseball would continue in a straight line forever until it came into the influence of some gravitational body or hit something and so forth. Now here's a definition of equilibrium. Equilibrium is when the net force, as it were, is zero. That is, it is moving at constant velocity, or it is at rest, and it's not there is no net force moving on it. The sum of the forces on it is zero. Then it's going to continue to move constant velocity, or it's going to continue to stay at rest. And so a body is at equilibrium when it is moving at constant velocity, or when it is at rest and there's no net force on it. Okay? So there's your definition of equilibrium, which will come into play later on, I think in Chapter 11. Okay, so we end this section of Young and Freedman's Chapter 4 by talking about something called inertial frames of reference. Now, you might remember the idea of a frame of reference from the previous chapter in Young and Freedman, at least, where it basically says a frame of reference is a coordinate system and in time. So you're timing a coordinate system. So an inertial frame of reference is basically a frame of reference in which Newton's first law works. So if you are in a frame of reference where a body of motion wants to stay at motion and a body at rest wants to stay at rest, then you are in an inertial frame of reference. Being on a train car, Young and Freedman show, is not an inertial frame of reference, because if the train car turns, you change direction, and so an inertial frame of reference is a coordinate system in time where a body in motion wants to stay in motion, and a body at rest wants to stay at rest. The Earth is not exactly an inertial frame of reference because it's rotating and because of gravity and all those things, but we are so little in relation to the Earth that it approximates an inertial frame of reference just in everyday life. Okay, so here's the final thing for this video. Two frames of reference are inertial in relation to each other if they are each moving at constant velocity in relation to each other. Now, you can't tell which one's moving if they're moving at constant. Has this ever happened to you where you're in a car and the car is parked and the car next to you starts to back out, and you for a second you can't tell whether you're moving forward or whether he's moving or she's moving backwards. So an inertial frame of reference, I have to say that they're moving at a constant velocity in relation to each other. The velocity of one is just the negative of the other. See the previous section in Young and Freedman, or the last section in Chapter 3. He talks about this sorts of things. I have a video on that. But we say that two inertial frame of reference are inertial in relation to each other if the relative velocity of the two, is constant. And there you have it, Section 2 of Chapter 4, Young and Freedman's University Physics, on Newton's first law: a body in motion wants to stay in motion, and a body at rest wants to stay at rest.